Hi class, so today we're going to be discussing properties of solutions. This is the last section in chapter 9, 9.6. So properties of solutions, we're going to start looking at the size and number of solute particles and how it affects a pure solvent in the way that it affects a pure solvent, such as adding antifreeze to water and the effects it has on the engine and temperature. So first, let's go over some things. Solutions. Solutions are transparent, means they're clear through, even if they're colored. They do not separate, so we cannot separate a solution very easily because it's very uniformly dispersed. Think of something like punch. We cannot separate it out unless we do other forms, but filtration doesn't work. Contains very small solute particles, ions or molecules, and because they're so small, they cannot be filtered because they just pass right through the membranes in the filter. Colloids, on the other hand, are medium-sized particles. They also are small enough that they cannot be filtered, so they can pass right through a filter, but they can be separated by a semi-permeable membrane, which captures medium-sized and larger-sized particles. Here's an example of some colloids. So you can see here we have, let's go down to something like food, mayonnaise, and homogenized milk. That is a liquid in a liquid. So those are actually made up of these colloids, these big clusters of medium-sized particles, as well as cheese and butter and blood plasma. So you can have a different, you can have an idea of example of colloids here. Suspensions are very large particles. And with very large particles, they do not go through a filter. So suspension and colloids are different. So colloids will not settle out, even though they're large. They will not sit at the bottom. They will stay in solution. And what some of the other things that aren't listed on this page could be proteins and a group of molecules or ions. But colloids are very large particles that will settle out of solution eventually. They can be filtered, and you must stir them in order for them to stay suspended in the solution. So this includes platelets, muddy water, calamine lotion. That's why they say to shake it, because this is settled at the bottom, and when you need to use it, you need to make sure you shake it so that it can be mixed in the mixture again, so that when you see on medicine and so forth that says shake well before using. So eventually will settle out, and they're very large. So here is a list of breaking down of solution, colloids, and suspension, and you can see the small, large, and very large, and if they settle out, and how can you separate them. Okay, so let's take a look. Properties of different types of mixtures. So the red cube or square is a suspension, a colloid is a triangle, and a solution is a circle. So if we look at A, suspensions settle out, so they will settle at the bottom because they're so large that they'll just settle out of water such as this, and eventually you can remove the water on top of it because it's just settled out. It's just so heavy. So that settles out, but the remainder, the colloid and solution will stay in solution, and they'll just, they'll stay above what is settling out. So B, suspensions are separated by a filter. So because they're large, they can be stopped in a filter, but solutions and colloids will filter through. Now, if you use a semi-permeable membrane, solution particles will go through, but colloids and suspensions do not. So it also depends on the size, and this is where we pay attention to the size of all of these particles, because if you need to filter something out, you need to pay attention to the size so it can either block it out or let it pass through. A mixture that has a solute particles that do not settle out but are too large to pass through a semi-permeable membrane is called a colloid. So it can pass through one, but not necessarily the other, depending on the size. It can pass through a filter, but not a semi-permeable, I cannot say this word, membrane. Now let's take a look at how particles affect, such as water, solvents, and the properties of it. So when a solute, which in this case will be non-volatile, means it does not evaporate easy, is added to water, the physical properties change. This is why we use antifreeze. The vapor pressures above the solution will decrease, the boiling point solution will increase, and the freezing point solution will decrease. These type of properties are called colligative properties, and this is hard for students to grasp, but they depend only on the number of solute particles, which means the concentration in whatever that is contained in, and not the actual identity of the solute. There's a lab that my other chemistry classes do. They do this lab, and they never know what the solute is, but they have to solve for everything, molar mass of it, and so forth, regarding freezing point, lowering, and boiling point elevation. So how does this work? Well, if you take water, we know that water boils at 100 and freezes at 0. But if you were to add something to it that breaks up these bonds to not allow it or prevent, let's say for boiling, it prevents those water molecules from evaporating, makes it harder for them to get through to the surface, then you increase the boiling point, which means the water has to get hotter, create more energy to allow those water molecules to leave. So think of if you've ever gone to a party and it's really crowded and you're trying to find your friends and you have to cross past all these people up to get to the other side of the room. That's the same thing as what's happening here. These non-volatile molecules or particles will block the water from leaving, and it makes it harder, so not as many will evaporate, and it causes the boiling point to increase. That's why you use antifreeze. It increases when to prevent water from boiling off. Vapor pressure lowering. It's the same thing here. So if it decreases the number of solvent particles. So if you have a pure solvent, water vapor, let's say water vapor it'll evaporate eventually, right? As if it's sitting there. But what if we were to add a non-volatile solute to it? The water will still evaporate off, but it will have to go, same as the boiling or evaporation, it will have to work harder to get out of the solvent. It'll have to get out of remove the solutes out of the way. So same thing as a crowded room. It has to pass all these solutes to work its way to get out, which slows the amount of water molecules that leaves, thereby lowering the vapor pressure because there's not as many water molecules above the surface. And as water molecules evaporate, they start creating their own vapor pressure above the surface of the solvent or solution. If it's pure solvent, it's just water. But if it's a solution, in this case, the vapor pressure is lower because the water cannot leave as easily. So there's not as many molecules building up right above the surface area of the solution. Freezing point lowering, it's the same. I know it says antifreeze. I put antifreeze there. What it does, it's the same as salt added to, we don't live where there's snow, but people, in cold areas, I'm sure some of you are common knowledge of this, they add salt to the icy roads to allow it to melt. It's the same thing. If you add a non-volatile solute to water, as our example, it prevents the water from freezing. The water has to work harder and release more energy, which means it has to go to a lower temperature than 0 in order to allow that water to come together as a solid. So it stops it. If somebody's trying to hold hands with somebody else and somebody's standing in the way, that's exactly what's happening. It's preventing them from coming together. And they have to work harder to hold hands. So here's an example. This is a regular solution of water. You can see, let's say that the normal freezing point of water is 0. The normal boiling point of water is 100. But if you add a non-volatile solute to the water, the boiling point has now gone up from 100 to maybe, let's say, 103. And the freezing point is no longer at 0, but let's say it's maybe -5 degrees. That -5 degrees is a big difference. It doesn't seem like it is, but, even here, living for 85 degrees to say something like 92 degrees, it's a big difference in temperature. You feel it. Okay, so number of particles. How does this happen? And how do, since we're not really worried about what the identity is, we're focused on the particles. So the number of particles affects the behavior of the freezing point depressions and boiling point elevations. So if we look at a solute that is a non-electrolyte, remember we were discussing non-electrolytes and weak electrolytes. A molecule will dissolve, but it dissolves intact. So something like a solute in antifreeze, which is ethylene glycol, is a non-electrolyte, and it'll dissolve in water. It'll go from liquid to aqueous, but that's all it'll do. And it's one whole compound. However, when you look at ionic compounds, they will break into, for instance, like sodium chloride, they will dissociate into two ions. So now you have two particles compared to one particle in water. This one would have, if you have another beaker, you have two particles that would impact the behavior of those water molecules, two people blocking the doorway to get out compared to one. So in this case, this has 1 mole that you could use, or you would have 2 moles of particles in solution. This is 1 mole of particle in solution. This has 2 moles of particle in solution. Even though it's 1 mole of sodium chloride, we're looking at the ions. This is 2 moles of particles in solution. So here's another example to help you understand. We're interested in the particles, and the more particles changes the behavior more. So do you want to have 1 mole of sugar? That will have 1 mole of sugar, 1 mole of particle to block maybe the exit if you're thinking of water trying to get out. Or do you want sodium chloride that will dissolve into two dissolved particles? Or do you want something like potassium sulfide that when dissolved, it actually dissolves into 3, even though it's 1 mole, it dissolves into 3 mole dissolved particles. 3 is better than 1, which is better than 2. So 3 would change the behavior even more than 2 and more than 1. So here's a little chart that's really effective, I think, that you don't necessarily have to pay attention to what the substances are because it's still just 1 mole. So let's look at pure water. Water is a freezing point of 0 and 100 Celsius, boiling. Then we have 1 mole here, but we don't really, honestly, it doesn't matter what this is. As long as it's a molecule that doesn't dissolve, that's all it needs to be. It needs to be 1 mole of a non-electrolyte. 1 mole will affect the freezing point of water, dropping it by 1.86 degrees Celsius and increasing the boiling point of 100.51 degrees Celsius. If you have 1 mole of an ionic compound, that's a 1-to-1 ion and ions, cation and anion, it's a strong electrolyte. So this is 2 moles. 2 moles will decrease the freezing point by negative 372 degrees Celsius and increase the boiling point to 101.02 Celsius. Now, if we have 3 moles of an ionic compound, does not have to necessarily be this, but it has to be a strong electrolyte, has to be an ionic compound, then it adds negative 5.58 degrees Celsius to that temperature, where now if water freezes, it has to reach this negative number in order for it to freeze, and it has to boil, or it has to reach 101.53 as the boiling point. So these particles will affect the behavior of the solvent, in this case as water. So let's do a problem. In northern United States during freezing temperatures, calcium chloride is spread on icy highways to melt the ice. Calculate the freezing point of a solution containing 0.50 mole of calcium chloride in 1 kilogram of water. This is molality, which we're not going to cover, but molality deals with moles over kilograms, even though that's not what they're saying here, and it's a small m, but that's what they're giving you here. So we're given a mole and we're given the kilogram of water. We need to find the freezing point of the solution. The solution involves the calcium chloride and the water. That makes up the solution. We know that calcium chloride is a strong electrolyte, so that's going to give us 3 moles of particles, and 1 mole of kilogram lowers the freezing point at 1.86. So, and then here we have T solution equals T water minus T difference. So what we're trying to find is the change in temperature here. We know that water is 0 degrees Celsius. So what we're trying to figure out is the temperature change, and that's going to give us the temperature of the solution, the freezing point of the solution. So, okay, so now that we know what we have, let's start working on the problem. So to determine the moles of solute particles, so this is a dissociation. It has to be dissociated from an ionic compound into aqueous solution. We have 3 mole of solute particles. However, we only have 1 mole of calcium chloride. So this might be a little confusing to some, but we're going to use the 1 mole on here compared to the 3 moles here. This is the freezing point for calcium chloride and what it ends up being affected by using the 3 moles. But we're going to stick with the 1 mole up here because that's how your book wants to do it. So I'm teaching you how the book wants it. It wants 1 mole and it's showing as the 18.6 for 1 mole of a non-electrolyte. I'm not really sure why, but I'm going to teach it the way the book is giving it to you. So we have that information. We have, okay, so determine the temperature change using the moles. So here we have the 0.50 mole of calcium chloride in 1 kilogram of water. So we don't need the kilogram of water. That's just extra information. We have 1 mole of calcium chloride, 3 moles of solute particles, and we're using the 1 mole of solute particles for 1.86 degrees Celsius. This ends up producing 2.8 degrees Celsius. Now this is the temperature change. This is the temperature change for this reaction, but that's not the final temperature. So now we have to plug that in. So we take the water temperature, which is 0. So this is the temperature of water minus the temperature change. And it gives us a negative 2.8 degrees Celsius. This is the temperature that is going to be the freezing point because of the fact that we calculated the change in temperature, but we couldn't use this temperature because this temperature is positive. If water freezes at 0 degrees Celsius, this is saying that water is going to freeze at 2.8 degrees Celsius, and we know that's not true. So we had to do an extra step in order to get that negative number to show that now water is going to freeze at 2.8 degrees Celsius. Okay, so now we're on to osmosis. Osmosis is water molecules that move through a semi-permeable membrane. So water flows from a lower solute concentration to a higher solute concentration. So water doesn't have any solute in it if you're looking at it pure. So that's low. But if you're looking at sucrose, this has a higher solute concentration because it has solutes in it. So the water is going to flow into the higher to try to equalize it out in a sense. So the concentration is not as high. So the level of the solution with the higher solute concentration will rise because as more water goes into it, it's trying to dilute it out in a sense. The concentrations of the two solutions become equal with time. So water will flow into the solution with higher solute concentration until the flow of water becomes equal. There's an equilibrium in both directions. Now what happens is that you see right here there's different arrows, but eventually over time there will be an equilibrium even though the water volume is higher where the higher solute concentration is. This creates a pressure, osmotic pressure, and it's equal to the pressure that would prevent the flow of additional water. So because this is an equilibrium, it's at a specific rate. We're thinking of maybe one water molecule moves in, another moves out. So this osmotic pressure prevents additional water being pushed in at a different rate. It's going to stay at this rate of what's happening here. And this osmotic pressure increases as the number of dissolved particles in the solution also increases. So there's a pressure to these flows of higher concentration and lower concentration areas. Reverse osmosis is a process where a pressure greater than osmotic pressure is applied to a solution, and it forces the flow of water to go from an area of lower water concentration to a higher water concentration. So this is what they use in desalination plants where they obtain pure water from seawater. So the seawater molecules and everything, ions, will be left on one side and the water will flush through. So here, osmosis that we're talking about from a lower solute concentration to a higher solute concentration. However, with this, we're pointing out that this is flows of water from an area of lower water concentration to a higher water concentration, and that would be the pure water. Pure water is going to have a higher concentration than something that has a higher concentration of solutes. Isotonic solutions. Because cell membranes in biological systems are semi-permeable, osmosis is an ongoing process. So in our bodies, we have solutions, and all these solutions have osmotic pressure. So they control the rate of what's going in and out. And this is what we call isotonic solutions. So they match. So isotonic So something that we're interested in is isotonic solutions. And what they do is they exert the same osmotic pressure as body fluids. And this is very important because we do not want to disrupt the way that the flow of our body is and what the pressure is going on inside of it. So two of the most, they've listed two important solutions, isotonic solutions that they use. And this is 5% mass by volume glucose. What this means is that it's 5 grams of glucose for 100 mils of solution. And this is 0.9% grams of sodium chloride per 100 mils of solution. So that's what these mean. So what happens is that if the osmotic pressure does not match, it's not isotonic. So first let's look at what isotonic. If in an isotonic solution, a red blood cell retains its normal volume. So the pressure inside and out is fine. There's no difference in osmotic pressure. But what if there is? If there is a difference in pressure, osmotic pressure, the concentrations do not match. For instance, you will get hemolysis. It's in a hypotonic solution. Water will flow into the red blood cell, causing it to swell and burst. And I'll give you examples of what all this means to make better sense. And C, crenation is in a hypertonic solution. Water leaves the red blood cell, causing it to shrink, and it looks like these kind of star pointy blood cells. It doesn't even look like a blood cell anymore. So a hypotonic has a lower solute concentration than red blood cells, meaning water flows into the cells by osmosis. And you can see they kind of don't have that circular in the middle the way that these do. They're kind of pushed out. This increase in fluid causes the cells to swell and burst. This is called hemolysis. Hypertonic, it's the same thing as we were talking about on the other page. In the first page, has a higher solute concentration than red blood cells, involves water going out of the cells, and this will cause them to shrink in size and look very dehydrated in a sense. So now let's take a look at dialysis. Dialysis is a separation process to separate particles. So the larger particles, like colloids, are separated from the solution particles and water and smaller ions and so forth. This is very important. So this is one of the reasons why we're discussing particles. All of this, is very important to removing waste from the body, and certain size particles, they can put up a certain filter, semi-permeable membrane, in order to block that from going back into the body or staying in the body. Okay, so let's take a look at some examples to help you understand isotonic, hypotonic, and hypertonic. So here we have, I've listed from the previous slide, two important solutions that are used that are isotonic. That means that they match the osmotic pressure of the body. And now we have different values. So here we have a 2% sodium chloride solution. So if we take a look over here, we can see that the isotonic is 0.9%. This is vastly different from the 2%. So if we were to take a guess here, then the 2% is higher than the lower. So what this means is it's hypertonic. That's going to mean that it's going to higher concentration than the red blood cells. Water's going to flow out of it because it's higher than what we have in our body. 1% glucose solution, but we normally have a 5%. So this is going to be B, hypotonic. Hypotonic, lower solute concentration than the red blood cells. Water's going to flow into, and that's going to cause it to maybe swell and burst. Number 3, same thing as 2. It's hypotonic. As you can see, it's lower value than the sodium chloride here. That's isotonic. So that's going to take B, lower solute concentration. Water will flow into it. And 5% glucose, that matches exactly what we have. That's isotonic. And that's exactly what shows up here. So, what happened here? This thing moved all over the place. I don't know why. When placed in each of the following, indicate if a red blood cell will A, not change, B, undergo hemolysis, or C, undergo crenation. So same thing if we look here, 5% glucose solution, that's here, that's A, it's not going to change. Maybe it'll be easier if I show you the actual values. So here we have 1% glucose. 1% glucose is lower than the 5% that we have in our body. So that's going to undergo hemolysis here. Water is going to flow into it, causing it to swell or burst. and 0.5 is lower. Same thing, water's going to flow into it. And then we have a 2% sodium chloride solution. That's going to undergo crenation because water is going to flow out of it. It's going to cause it to be dehydrated in a sense. Okay, and that's it. And here's an overall map, or a map of showing of all the steps that we've covered. And hopefully this will make sense now if you look at that. Okay, thank you.